Welcome to part 2 of my video series on how to model a short sleeve in OpenFOAM. This video tutorial that consists of a total of 5 videos. I concluded part 1 of this tutorial with the prospect of showing you in part 2, which is this video, how to create the mesh for the short sleeve we want to model later, and we do this by transforming the sloshing tank 2D mesh into something we want. And we're going to use it. We're going to do this by using the M4 script, which is a very old scripting language. And in order to get a feeling how this works, we're going to open the script file, and it's under constant polymesh blockMesh dict.m4, typing gedit constant polymesh blockMesh dict.m4, opens the file, and it's always a good idea to save it as a backup copy in the beginning. For example, I can name this my blockMesh dict.m4, enter. So if I screw things up, I will always have the genuine version. How do these M4 macro files look like? We can see in the beginning that we have an area where we have general M4 macros. There we don't have to change anything. Just if I go through the commands real quick, we can see that we change the quote command into the actual C++ quote command that our blockMesh dict will later then also understand. We define a function calc that sources mathematical functions in order and makes them accessible for us later in the process. We define a variable called vcount and put it to 0. And most important, I think, is this line, where we define a function that is called the vlabel, and this vlabel actually enables us to address all the vertices that the blockMesh later constrain with actual labels. And this is helpful because by doing so we don't need to keep track on which number the current vertex we want to address has, but instead we can simply assign them names, which makes it quite a lot more easy to handle. And the following functions are functions to produce shapes. We have an hex 2D, which is sort of a cube, or sort of a cube in 2D, or a slice of a cube, whatever you want to put it. And this is nothing less but that you at first address 4 vertices that make up the back of this slice, and then the 4 vertices that make up the front. And as we shall see later, when we create our own M4 file, you can actually address these vertices with their labels, which makes it very convenient to use. And the same basically you can do for a quad 2D, which is helpful later on when you assign the boundaries of the domain and tell the blockMesh which faces should belong to one patch. Last but not least, 2 functions that return a front quad and a back quad, and these are helpful in order to assign the front and back patch later in our domain. Okay, but going back to this very nice figure that I drew in order to show you how this actually works. What you can see here are the dots. These are the vertices that actually constrain the entire blockMesh domain. And for those of you who are familiar with how blockMesh works, normally the vertices are addressed by their numbers, and the first vertex you define gets assigned number 0, the second number 1, the third number 2, and so forth. And here in this case, the vertices, you have always 2 pairs of vertices, one in the back, which is the first number here, which is the 0, and one in the front, which is 0 plus 8, because you have 8 vertices in the back, so the first vertex in the front will have 0 plus 8, aka 8. And you can see this for all the other, this is true for all the other vertices too, because then you have 1 is paired with 9 and 5, for example, is paired with 13, so we always have the difference of 8 between the two numbers. Okay, but you don't have to be super smart to see that this is clearly not the domain we want. But one more important thing I'd like to stress: when we look at the picture, you have this combination of letters here in front. And going back to the M4 file, you can recognize that these combination of letters you can also find here later, which is basically when you address the vertices. So basically what was done here with this M4 file was the idea to give each vertex its own name. And now the smart people of you think, well, how can that be? You only have one string and two vertices are assigned to this string. Well, that depends on whether you actually look at the vertex in the back, then this becomes BLUCT, or you look at the vertex in the front, then this becomes FLUCT. And this normally you don't have to take care of yourself. The functions just normally do it for you. As you can see here, depending on whether you address a front quad, it will automatically add an F in front of the string, and if not, then and if you address a quad in the back, and it will add a B in front of the string. And if you define something that has front and back, it will add the B at the particular position and the F also at the particular position, which you can also see in this line. So going back to the figure, this would make vertex number 2 BLUC, vertex number 10 FLUC. I hope this helps you in the following to understand a bit more easily how actually the vertices are being addressed. Okay, but now let's look at what we actually do want to create. And this is very generous of this tutorial to be so much alike the one we want to create, because we have a total of 16 vertices in the slushing tank 2D, and also have a total of 16 vertices in our shotSleeve tutorial. And the only thing is we have to label them differently, and we also have to make sure that they are at the particular positions in space where we can actually want them. And one more convenient thing about scripting is that you only need to define the variables you need. So in case you want to decide later to have the piston not at position -300 but at -400, you have to only adjust the value of one variable, which is the piston, and then all the rest will be taken care of. And this is also why I drew this picture, because we can see here that we basically only need 3 independent variables to constrain our entire domain. We have in z direction, we have the values z piston, which I put at 300. We have the boundary between the moving area and the fixed area, which I labeled z boundary moving fix, which is here, which is at position z20, and we have the end of the sleeve, which I put at z0. And in y direction we also have 3 levels. We have the lower end of the cylinder, I labeled it y cylinder down or y sil down, the upper end of the cylinder, which I labeled y sil up, and finally the outlet, which I labeled y outlet. Okay, so let's go ahead now and put all this information into the M4 dictionary, and we start by defining our geometry constraints. One more thing, I'm an engineer, so I'm used to type in all the values in millimeters. That's why I use this convert to meters entry, and then each value I type in anywhere in this dictionary will be multiplied by 1e minus 3, so basically transformed from millimeters into meters, because this is very important. OpenFOAM always works in SI units, which will mean meters in this case. Okay, Z piston, I said it was at 300. I'm going to get rid of the name this position Z direction. Next is the boundary fix. This was at minus 20. So I've got a minus here, I just realized. Okay. Sorry for that. And finally, last Z coordinate will be Z end of leaf. Z end of leaf. And put this at 0. It's not good. Not gonna use the epis. I'm gonna try to decide to omit the apostrophe here. Apparently this causes problems. Alright, and next thing to be done will be to define the y values. Y cell down, which was at minus 30. So of course will be the upper end, which I labeled y cell up. It was 30. And finally y outlet, which was at 50. Okay. Okay, what else do we need? We of course need one coordinate for the back and one for the front, and we can do this by naming them xb, and we'll put this xb at minus 5, and of course we need another xf coordinate for the front. Okay, so with these 8 parameters, our domain should be fully constrained. We should, however, add some more variables for determining the spacing of the mesh, aka how fine the mesh shall be that we want to produce. And for this we can use these n parameters, because n for number, because the block mesh will then also need this information to be provided in the way of naming the numbers of cells to be put into a certain area. And we can start with n diameter. In this case I chose to put 15 cells cross-sectional in the diameter. Number of cells in diameter. Next one was n moving, and here I picked 35, which is about equal to a cell spacing of cell length of millimeters in this direction. Numbers of the cells in the Z direction. thing will be fixed. There I put 5. Now this is actually in Y direction. In the Z direction it will be the same as in diameter. Okay, then outlet height. For the outlet height, it shows also 5 cells. And the outlet, and last but not least, thickness, which is fairly easy in 2D simulations because you only put one here. It's 2D. Okay, this is all we need for now. Derived parameters, we don't need any, so I can highlight this entire paragraph and delete it, and we can then move ahead to defining the vertices. And what we need to do now is put the particular coordinates in here and also give them the proper labeling. And for this I refer once more back to this figure, and here we can see that we start with PD, then use PU, and then move forward to IBLL, and also where at which positions they all are. So let's get started. XP can stay, and we start with BP PD, which means piston down, and this will be at Y sill down and Z piston. Next one will be PU, which I name for piston up, which will be at sill up. Z piston remains. Next was IBLL, which is at Y sill down, Z boundary moving fix. And at IBLL for internal boundary lower left. Then the next is IBUL, internal boundary upper left, which is at the same Z position. But at Y sill up. Next one will be outlet left then. Set Y outlet, of course, and once more Z boundary fix. Then comes lower right, set Y sill down and Z end of sleeve. Next one is IBUR, internal boundary upper right. So just at Y, cell up, and Z end of sleeve. And finally the outlet or back outlet right, just add Y outlet of course, Y outlet of course, and the end of sleeve again. Okay, just a quick plausibility check. I should have 3 vertices now at end of sleeve, check. 3 at boundary and moving fix, check, and 2 at Z piston in Z direction. And I should have 2 at Y outlet, 1, 2, and 3 at Y cell up, 1, 2, 3, and 3 again at Y cell down, 1, 2, 3. So that looks good until here. What I can do now is that I once more need the same vertices also for the front. I have so far only created it once for the back. I just do this by replacing this paragraph, and I just replace the B in here with an F. So it's quite convenient and quite fast, and also I have to do the same in here. It's a bit more annoying as they're not aligned, but still it's manageable. Okay, these were all the vertices, and we can now proceed to actually creating the blocks. And with the blockMesh, it's a bit tricky, or it can be tricky for those who are not very familiar with it, how to, in which order to place the particular vertices in order to create a sound blockMesh. But don't worry, I'm going to help you, because I've already sort of figured it out, at least for this case. And the thing is that you always stick to the rule that if you are inside the cell, you have to go, if you define a block, you have to be in one plane for defining the first 4 vertices, and then only with going from vertex 4 to vertex 5, or as they label 3 to 4, then you can go into the 3rd dimension. And inside this first plane you always have to order the vertices in a way that you walk from one to another in a clockwise direction while looking from a point inside the cell. It is a bit difficult, and it takes a lot of imagination to figure that out, but once you've done it a few times you will get more and more used to it. Okay, but going back to this figure, what I just said means that if we want to start at PD, for example, and now we look at the back, so basically we look from inside the cell onto the face, so we have to walk in a clockwise direction, means we need to go from PD to PU to IBUL to IBLL in order to create our first block. So this is just what we're going to do. PD, PU, IBUL, IBLL. And the fact that they actually are in 2 separate planes, in the front plane and the back plane, this I don't need to address, because this is taken care of by this function, which takes in the values from 1 to 4, which is shown here by these $1 to 4 signs, and adds a B to them, and also an F, and by doing so it creates the 8 vertices which the blockMesh needs. Okay, so by going from PD to PU at first means that our x1 direction is actually where in the cross-sectional direction, so we have to put NB diameter here, N diameter, and the second direction we walk along will be in the way that the piston moves, so we put and moving here. And finally, third dimension always is thickness. Alright, good. So this was our first block. Second block is quite the same. I'll start, for example, at IBLL and then walk again in a clockwise direction from IBLL to IBUL to IBUR and finally to LR. So let's just do that. So that was that. First direction, x1 direction, was again the one in the direction of the radius vector. So the diameter here. Diameter. Second direction was in the z direction, so we put n fixed in here, and third direction was thickness again. Okay, second block done. Alright, let's move to the third block, which is this one, and here we go from IBUL to OL to OR, then back down to IBUR. IBUL, OL, OR, IB, OR. Okay, that's that. And outlet, that height, and fixed, because we want to have the same spacing as the cells underneath, and thickness. Okay, that was that. So the only thing left to be done will then be to assign boundary. For doing so, we have to make some modifications here. With the patches, I don't like to work. We want to use a boundary, and we want to start with the moving walls, which will be the face, the piston addresses. Moving walls, I have to make some modifications here. And moving walls will of course be of type wall, and will include faces, and the faces we label and we name the following, semicolon at the end, and also close the subdictionary. The faces that make up moving walls are basically only PD and PU. So we only have to put them here. And all the other stuff we don't need, because this patch is rather small, so we can delete it. Okay. It's good. One down, 3 to go. And the easiest would probably normally just be to rename, copy this subdictionary, paste it back in, just rename it. Here, 2 more slip walls, and the slip walls are faces that are made up by PU and IBUL, and the other face which is the same but just below, so i.e. PD and IBLL. Okay. Just careful here. Yeah. Remember the clockwise direction. So I may wanna swap these. Okay, slip walls done, basically. Next one will be fixed walls. Fixed walls, also type wall, and for the fixed walls we'll have of course the IBUL, OL, we'll have the IBUR and IBUR and LR, and we'll have the OR, IBUR, and finally we will have the LR and IBLL. Okay, that should be it. The only thing that's left now will be the outlet. Outlet also only consists of one phase. And what is different is that this is not a wall but a patch. And the outlet has the two faces OL, or the two vertices that make up the face, and OR. Okay, that's basically it. The patches we need to assign. One more thing, because this is a 2D case, this is of course the entire front and back. Front and back, I'll call this type empty. Empty. And the faces, it consists of 3 front quads, and 3 back quads. Delete this. Okay, so let's see what we need to put in here. Of course, PD, quad of block 1, PU, IBUL, IBLL. And then of course for the second block, IBLL, IBUL, IBUR, and LR. Last block, IBUL, OL, OR, IBUR. Okay, I think it will be just easier if I just copy and paste this below, because we also need the same for the back. Paste, just name this back. Okay, so this is our entire M4 file. Save it. So the only thing that can happen now is that we actually put some typos in, and this is particularly difficult for all these variables. So I'm going to do a quick check. I'm going to look for Z piston, and I can see here that I have 5 matches, 1, 2, 3, 4, 5, which are the 2 points in each plane and one where I initialize it, so that looks rather good. Then I could check moving fix. I got 7 matches, 1 where I initialize it, and 6 for the usage, and I have 3 vertices as I outlined in the beginning where I need to use this variable. Okay, last one is end leave, and I once more have 7 matches. Looks good. Same for the y coordinates. Y still down, 7 matches. Sounds good. Same for y still up, also 7 matches, and y outlet should be 5 matches, and there it is. Okay, that looks very good. What I can also check are the variables for the mesh spacing and diameter, 2 matches. Look at this, and I already found a typo, so it's good that I checked. And diameter, 2 matches as it's supposed to be. And moving, 1 match, which is okay because we only use that in one block 0 to be exact. And fixed, we have 3 matches, which is also correct. Outlet height, I only need for 1, so 2 matches is okay. And finally, thickness. Why do I have 4 matches? Okay, this is about right because we use it in every block and we initialize it once. Alright, the only thing that could be is that I have typos with the labeling of the vertices still, but I'm going to find out once I actually try to do the blockMesh dict. Okay, let's leave it with that for one thing and go back to the terminal. Control Z, BG, and Control Z, and BG. Put it to the background, and I can try if my M4 file works. So M4 says that I'm going to execute an M4 script, and this sign that redirects the output, this smaller sign redirects the output to the file that I put in here, and I want to have it in constant polymesh blockmesh dict. Enter. Okay. I have execute blockmesh now. At least terminates as supposed, and I also have the right dimensions and no errors, so I guess I was pretty lucky with the creation of the blockmesh. And one more thing, I also have the patches that I wanted, and I can look at it in partII. Seems to be taking some time. Make sure that you uncheck these boxes here, because it won't find the proper boundary field entries for the patches we just created, because they still correspond to the old case, the sloshing tank 2D. But we can load the internal mesh, hit apply, and if you turn, or if you take one of these viewings, that you see that you have exactly the shot sleeve as you wanted it, and as I showed it previously to you in the video. Okay, this concludes the second part of my video tutorial, and in the next part, part 3, I will show you to do all the necessary adjustments to actually perform the mesh motion as you want it to be, and this will also include heavy use of the toposet utility in OpenFOAM. Thank you for your attention, and see you back in part 3.